Welcome back to an introduction to real analysis. We continue section by section. We're now in chapter 2, section 2, facts about limits. What are we going to discuss today? Well, we're going to go over a whole bunch of results regarding limits of sequences. The thing to focus on here is A, of course, what the actual results are, but also how we are putting the proofs together. A bunch of examples of specific sequences with limits are also going to be included. So first, let's take a look at limits and inequalities. A very basic lemma we're going to establish is what's called the squeeze lemma. It allows us to show convergence of sequences in difficult cases if we can compare in a certain way our unknown sequence to two sequences whose behavior we do know that can squeeze down on our sort of test sequence. Specifically, the sequence of interest is going to be trapped between two sequences that have to converge to the same thing. So here it is, the squeeze lemma. Suppose you have three sequences, an, bn, and xn, so that xn is always in between an and bn. So here, xn is going to be the sequence we want to show something about. It is squeezed between an and bn, sequences that we presume we know have limits. And more specifically, the limit of an and the limit of bn must be the same number. So not only do an and bn have to squeeze on x, they also have to converge, and they have to converge to the same thing. Under these hypotheses, xn must converge to the same thing as well. So let's take a look at the proof. Okay, so our goal is to show that the limit of xn is equal to L. So we're assuming that an and bn have limits and are equal to this number L. So we're going to start off our proof recalling the definition of the limit of a sequence being L. It begins with, for all epsilon which are positive, you have to prove something, so let epsilon be positive. Now, since we know that an and bn are converging to L, there must be an m1, so that past that index, an is within epsilon of L. Therefore, an has to be at least as large as L minus epsilon. But similarly, because bn is known to converge to L, there is another index, capital M2, so that past that index, bn is within epsilon of L. Specifically, it must be less than or equal to L plus epsilon. So we do a pretty standard thing. If we have two different cutoff indices past which desired behavior occurs, we take a new cutoff past the maximum of those two. So if n is bigger than both m1 and m2, an is known to be at least as large as L minus epsilon, bn is less than or equal to L plus epsilon, and xn is in between the two of them. Specifically, xn is in between L plus or minus epsilon, meaning the absolute value of xn minus L is less than or equal to epsilon. Okay, a word of warning. In the squeeze lemma, we assumed that an was less than or equal to bn, and they both had the same limit. A lot of people come to a sort of incorrect conclusion here, that we need something like an and bn are on opposite sides of this limit. That's not quite the case. An must be less than or equal to bn. They both have to converge to L, but there's no inequality regarding L here. Okay, just because the two sequences obey an inequality and converge to the limit does not mean the inequality applies to that limit somehow. Let's take a look at an example. We'll show the limit as n goes to infinity of n to the minus 3/2 is equal to 0. Now note, for all n, we can squeeze 1 over n to the 3/2 is going to be less than or equal to 1 over n, because n to the 3/2 is bigger than or equal to n, but certainly none of these are negative. So our new unknown sequence is squeezed between two sequences. On the left, 0 is a constant, so as n goes to infinity, the limit of 0 is 0, and we've already seen that the limit as n goes to infinity of 1 over n is also 0. So 1 over n to the 3/2, our new unknown sequence, has been squeezed between two sequences, the constant 0 and the sequence 1 over n, both of which converge and both of which converge to 0. So by the squeeze lemma, our unknown sequence, 1 over n to the 3/2, must also converge to 0. All right, let's take another look at an example very similar to the last one. We'll show the limit as n goes to infinity of the sine of e to the n plus log of n over n is equal to 0. Now, sign is always trapped between plus or minus 1, and it doesn't matter what the input is. Basically, this e to the n plus log n is a bit of a red herring. The sign of absolutely anything is in between plus or minus 1. So our sequence is in between plus or minus 1 over n. And again, we can take the limit as n goes to infinity. Minus 1 over n goes to 0. 1 over n goes to 0. So our unknown sequence has been squeezed between two sequences that are both converging to 0. So by the squeeze lemma, our unknown sequence must also converge to 0. On to lemma 2.2.3. Suppose you have two sequences, xn and yn, and they both converge. And we have this inequality between terms of the sequence. Xn is always less than or equal to yn. Then you conclude that the limits must obey the same inequality, x is less than or equal to y. It is important here that this conclusion allows for the possibility of equality. We'll talk about that more after we prove this. So let's go ahead and prove it. Let epsilon be a positive number. We know past a certain point, the terms of xn are within epsilon over 2 of x. Also, another index cut off past that point, the terms of yn are within epsilon over 2 of y. Doing what we've done before, if we go past both of these numbers, we will have both of these inequalities. Specifically, x minus xn is less than epsilon over 2. In other words, x must be less than xn plus epsilon over 2. But also, negative y is less than minus yn plus epsilon over 2. Now what we're going to do is we're going to add these together. We get x minus y is less than xn minus yn plus epsilon. But remember that xn is less than or equal to yn. So xn minus yn cannot be a positive number. So here I have something that isn't positive plus epsilon that only makes it smaller. So x minus y is less than something that is less than epsilon, epsilon plus this non-positive number here. In other words, x minus y is less than epsilon. Remember that epsilon was totally arbitrary. So if x minus y is less than an arbitrary positive number, x must be less than or equal to y. As a corollary, suppose the limit of xn is x and every xn is bigger than or equal to 0, then the limit must be bigger than or equal to 0. Similarly, if the limit of xn is x and xn is trapped in between two constants a and b, the limits must obey the same inequality. This is absolutely immediate from the previous result. Here, just compare xn to the constant sequence 0, which converges to 0, so whatever that limit is must inherit the same inequality. And here we're comparing to the constants a and b. Now, a word of warning as promised, the inequalities cannot be replaced with strict versions. For example, suppose the limit of xn is x, the limit of yn is y, and we know strictly every xn is less than yn. You do not conclude that the limits have the same strict inequality, and we've already seen such an example. Negative 1 over n is negative, 1 over n is positive, so every term has these inequalities. But if you take the limit as n goes to infinity, both of them go to the same thing, 0, and you get equality here. So it was very important in the conclusion of that result that the inequality allowed for the possibility of equality. Let's take a look at algebraic operations on limits. So limits interact very nicely with standard things like addition, subtraction, multiplication, and division. We're going to present a few results and prove them in order to gain proficiency using the formal definition of the limit. So here are a bunch of propositions combined into one slide. Suppose that the limit of xn is x, the limit of yn is y. So specifically, we have two sequences that do converge. Then, the limit of xn plus yn is x plus y. The limit of xn minus yn is x minus y. The limit of the product is the product of the limits. The limit of the quotient is the quotient of the limits, provided you don't have any division by 0 issues. Proposition 2.2.6. If every term is bigger than or equal to 0, you can take the limit of the square root and obtain the square root of the limit. And in proposition 2.2.7, the limit of the absolute value of xn must be the absolute value of the limit. Okay, let's start proving. The first item, the limit of the sum is the sum of the limit. So we know that xn is converging to x and yn is converging to y. Here we have a new sequence. We want to show it converges to this number. So we go through the definition of the limit. We say let epsilon be positive. We know that past a certain point, xn is very close to x, yn is very close to y. We get two different cutoffs for each of these sequences, but if we simply go past the maximum of the two, we will get both of these inequalities. Okay, so we just go through that construction again. Then by the triangle inequality, we have both xn minus x less than epsilon over 2 in absolute value, yn minus y less than epsilon over 2. We need to now compare xn plus yn minus x plus y. Okay, so if we want to look at xn plus yn minus x plus y, we distribute, rearrange, use the triangle inequality to get both xn minus x, yn minus y, but we are sufficiently deep into the sequence where both of these are less than epsilon over 2. So overall, we have less than epsilon. And there's item 1. Okay, we're skipping item 2. The only difference is that a plus is replaced with a minus. That's left as an exercise. Let's go on to item 3. Let epsilon be positive, and we're going to pick a k. This is going to become clear as we work through the proof why we picked this. So the limit of xn, the limit of yn in absolute value, epsilon over 3 and 1. Out of all of these numbers, whichever one is biggest, I'm going to let that be k. Now pick a capital M so that if we go sufficiently deep into the sequence, the distance from xn to x is less than this positive number. The distance from yn to y is less than this positive number. And again, because xn is converging to x for sufficiently large indices, this may be less than any positive quantity. Similarly over here, just take the maximum of the two cutoffs. You can get both of these to occur. Now we need to start estimating what is the absolute value of xn, yn minus xy. And remember, our goal is to get that this absolute value is less than epsilon. All right, so we picked our k. We know that for little n sufficiently large, xn is as close as we want to x and yn is as close as we want to y. And we picked as close as we want to be epsilon over 3k. Now take a look. We want this to be less than epsilon. Xn we replace with xn minus x plus x. Yn we replace with yn minus y plus y. Now we start distributing out this whole thing. You get xn minus x times y, x times yn minus y, and then you can move some various terms over here. This is just a matter of algebraically verifying. By distributing out everything and seeing what you get, these two things are equal. Now we can use the triangle inequality several times. 1 term, 2 terms, 3 terms, so less than or equal to the first absolute value plus the second plus the third. Now we start breaking up the absolute value of a product into a product of absolute values. Okay, so here's where we are right now. We want this to be less than epsilon. We have it less than or equal to this enormous construction here. Okay, so here's what we had at the end of the previous slide. Now, each of xn minus x and yn minus y are known to be less than epsilon over 3k, but also the absolute value of x and the absolute value of y were one of the choices and k was the maximum. So each of these two things is also less than or equal to k. So this is less than epsilon over 3k, this is less than or equal to k, epsilon over 3k, k, epsilon over 3k, epsilon over 3k, and there's what we have. The distance from xn to yn compared to xy is less than this construction here. But also, k is at least as big as epsilon over 3. That gives me that epsilon over 3k is less than or equal to 1. So this epsilon over 3k is less than or equal to 1. And since k is at least as large as 1, this epsilon over 3k is at least as big, is less than or equal to, epsilon over 3. So overall, you get 3 different terms of epsilon over 3, or the distance from xn, yn to xy is less than epsilon. Which means we can move on to item 4, the limit of a quotient. First, we're going to consider the special case of where xn is a constant sequence. Okay, so we just need to prove that the limit of 1 over yn is 1 over y. We're going to assume that every single term of yn isn't 0 and the limit isn't 0, so we do not have any division by 0 issues. So let epsilon be positive. So similar to the previous proofs, we're going to pick m large enough so that the distance from yn to y is less than this positive quantity, the minimum of these two things. Whatever this is, the absolute value of y over 2, which isn't 0, because remember we are assuming that this limit isn't 0, but also the absolute value of y squared times epsilon over 2. And again, the reasons why we're making this interesting choice will become clear. Okay, so each of those values is positive, so we can find this cutoff. All right, so we have picked a cutoff past which we have the following inequality. So we go through a sort of trick we've done many times. The absolute value of y is equal to it plus and minus the same quantity. We then consider this to be one number, this to be a second, use the triangle inequality. Now observe that the distance from y to yn past a certain point is less than the minimum of these two things, so it's definitely less than that. And here we have yn by itself. Okay, so if I subtract the absolute value of y over 2 from both sides, on the left we have this, on the right we have that, we just get that the absolute value of y over 2 is less than the absolute value of yn. So we reciprocate this and we get that the absolute value of 1 over yn is less than 2 over the absolute value of y. So now we know past a certain point, the absolute value of 1 over yn is less than 2 over the absolute value of y. Just to refresh, we're proving item 4 here in the special case where xn is 1. So we really want 1 over yn to be converging to 1 over y. So now we can get to the real goal here. We need to somehow understand the distance from 1 over yn to 1 over y. We want this to be less than epsilon. Give them a common denominator, split up the denominator into the product of two terms, and what do we know? This 1 over yn is less than 2 over y. Now we also have that the distance from y to yn is definitely less than the absolute value of y squared times epsilon over 2. And now it's clear why that was in there. This absolute value y squared cancels both of these, this 2 cancels that, and this epsilon stays behind. What have we shown? The distance from 1 over yn to 1 over y is less than epsilon. So we have proved item 4 in the very special case of xn being constantly 1. Okay, so now we can derive 4 just by using item 3. We replace xn over yn with xn times 1 over yn. We've already proved item 3. The limit of a product is equal to the product of the two limits, so we split these two things apart. We already know this is converging to x, and we've proved this converges to 1 over y, and x times 1 over y is just x over y. Incidentally, this is a pretty common trick in dealing with proving stuff regarding quotients of arbitrary objects. Instead of considering it to be a quotient of two arbitrary things, you split it up into a product times 1 over whatever the denominator was. The point being that instead of dealing with quotients in general, if you can merely handle 1 over something, just reciprocation, then apply a product rule of some sort, you can derive something about quotients in general. At this point, we can make a comment about polynomials and ratios of polynomials and how they interact with limits. So if you look at item 3, it says the limit of a product is the product of the limits. Well, what if you take the same sequence? Xn and yn are the same thing. Then the limit of xn squared is just the limit of x squared. You can then inductively get the same thing for any positive integer power. The limit of xn to the k will be whatever that limit was, x, to the k. Throw in item 4, that allows us to do reciprocation, so you can get the same result, the limit of xn to the k is equal to x to the k, even when k is a non-positive integer. Now you throw in items 1 and 2, you can add and subtract. We also know that you can multiply limits by constants without affecting the value. I mean, the constant factors out. And now we can conclude that for any polynomial, the limit of p of xn is p of x. So polynomials interact with limits in a very straightforward way. Then, since we already know quotients work through item 4, if you have the ratio of two polynomials, you'll get the same thing. Well, we just remarked that polynomials and rational functions interact very nicely with limits. What about arbitrary powers? Look at prop 2.2.6. This is basically raising something to the 1/2 power. So let's begin with a little bit of algebra. We're going to need to compare the square root of xn to the square root of x in order to show that this limit is what we want. So we do the pretty standard trick of multiplying by the algebraic conjugate. The benefit here is that this numerator, xn minus x is now going to be something that we know something about because our hypothesis is that xn is converging to x. So the denominator is a little weird, however, root xn plus root x. If x is 0, this becomes tricky, whereas if x is not 0, then it's much simpler. So we're going to do a proof by cases. Okay, every xn, by the way, is bigger than or equal to 0. That was one of the hypotheses here. So the limit x can't be negative. We don't have an issue in that sense. Continuing the proof, the easy case is assuming that the limit x is positive. Now let epsilon be positive. There is a cutoff point past which the distance from xn to x is less than any positive quantity, and we're going to replace it with epsilon times root x. Because x was positive in this assumption, we haven't stuck a 0 there. So, using the same algebra from the previous slide, we get that the distance from root xn to root x is equal to this quantity here. Now we know that this numerator may be replaced, is less than epsilon times root x. Okay, also, both root x and root xn are non-negative, so the absolute value in the denominator isn't really accomplishing anything. In the numerator, who knows, but in the denominator, we have two non-negative roots there. So we drop the absolute value in the denominator. Our numerator is less than epsilon times root x. And observe that root xn plus root x is bigger than or equal to root x, because this is bigger than or equal to 0. So overall, this quotient is less than or equal to the numerator unchanged and the denominator just with a root x. Root x's cancel, and we just have an epsilon. So in the case where x, the limit, is positive, we're done. What if that limit x is 0? Okay, in our previous proof, we had a root x in the denominator. That would be bad. So we can more simply just find an m so that past that point, the distance from xn to x is less than any positive quantity we want, and we're going to use epsilon squared. Now x is equal to 0, so I can ignore this x here, and we simply get that the absolute value of xn is less than epsilon squared. Hit it with a square root. The root of xn is less than epsilon. On the left, by the way, this absolute value for xn is not necessary because our hypothesis is that the xn's are non-negative. So now you can simply say that the absolute value of root xn minus root x, well, root x is 0, because in this case x is 0. Because xn is non-negative, that square root is non-negative, we can drop the absolute value, and we've already seen that we have a less than epsilon. So the case of x equals 0 also works out. Overall, Prop 2.2.6 is therefore proved. This result, it is worth mentioning, does hold for any rational power. If the limit of xn equals x, then if you take a rational power here, you end up with things working out like you want. That can be shown. We're just going to leave it as a fairly challenging at this point exercise. Moving on to the final item here, proposition 2.2.7. The limit of the absolute value of xn is equal to x. We're going to need the reverse triangle inequality here. So here it is, item 1 of corollary 1.3.3. So we're going to use it in this form right here, where our x's we're replacing with xn's, and compared to the way the corollary is written, we replace y with x. Now let epsilon be positive. We know that past a certain point, the hypothesis tells us that xn is within epsilon of x. But xn minus x here is bigger than or equal to this absolute value. So we end up with this being bigger than or equal to that. Overall, the absolute value of xn minus absolute value of x is less than epsilon, which is exactly what we needed in order to prove that the absolute value of xn is converging to the absolute value of x. Do want to point out something, however. Prop 2.2.7 is definitely not true in the converse. What do I mean? If the limit of the absolute value of a sequence exists, that does not imply that the original sequence converges at all. And we've seen an example. Suppose xn is just alternating between plus or minus 1. Then the absolute values are all 1, and that definitely is a constant sequence, has a limit, 1. So if we have the sequence that is plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. If I hit it with an absolute value, that does converge to 1, but the original sequence is not converging to anything. So Prop 2.2.7 says if xn converges to x, then the absolute value of xn converges to the absolute value of x. Do not attempt to run that in the converse, however. Okay, more words of caution about attempting to run things in the converse. So all of these propositions, the given, the hypothesis, is that the limit of xn is x and the limit of yn is y. Don't, in general, try to run these things backwards. Just because certain limits of sums, differences, products, quotients, etc. exist, don't attempt to conclude original limits exist as well. So just verify algebraically that n minus n squared over n plus 1 is always equal to 1 over n plus 1. So because this is equal to that, this limit as n goes to infinity is 0. So the limit of n minus n squared over n plus 1 must be 0. But the limit of n and the limit of n squared over n plus 1 on their own do not exist as real numbers, and their difference is definitely not going to just be easily computed. They don't even exist as limits. Within the extended reals, they're both infinite, and you would end up with infinity minus infinity. That's indeterminate. So the limit of the difference is 0, but the individual limits are not real numbers. Let's take a look at some recursively defined sequences. This is going to lead to some interesting examples. So now we know we can interchange limits in algebraic operations. So we can do a lot of different things. So one such class of sequences that we can now take limits of are recursively defined. In other words, sequences where knowledge of the previous terms tells you what the next value is. Let's take a look at an example. Suppose we recursively define a sequence by saying x1 is 2, and beyond the first term, you achieve the next term by computing the previous term minus previous term squared minus 2 over 2 times previous term. So this is just an algebraic operation on a term of the sequence that gives you the next one. So we will attempt to determine if there is a limit, and if there is, what it is. So first we should guarantee that we can actually compute terms of this sequence. We are dividing by xn. If xn is ever equal to 0, we've got a problem. So let's verify that no term of the sequence is ever equal to 0. So here is our recursive formula at top, and we are attempting to verify that we never get a 0. So first of all, if we give this a common denominator and simplify, xn plus 1 is just xn squared plus 2 over 2xn. So now, assuming that one term xn isn't 0, up here we get at least 2 over not 0, and the next term is also not 0. So definitely none of the terms of this sequence are equal to 0. Okay, so we never have a problem of division by 0, so all the terms exist. Now we can move on to actually showing that there is a limit. We're going to rely on the monotone convergence theorem because it will work. I mean, not every sequence is monotone, but this one is. All right, so let's try to show this sequence is monotone decreasing. Since xn plus 1 minus xn is just this term here, negative xn squared minus 2 over 2xn, to show that this is decreasing, we just need this difference to not be positive. And so we have a minus something. So if we can simply show that xn squared minus 2 is bigger than or equal to 0, we will have a monotone decreasing sequence. So let's take a look at xn plus 1 squared minus 2. We really want to show this is bigger than or equal to 0. On the previous slide, we had shown that xn plus 1 is xn squared plus 2 over 2xn. So we're just subbing that in here. Now we have some kind of tedious algebra to do. First of all, this denominator will just square to 4xn squared. Multiply this out, you get xn to the fourth plus 4xn squared plus 4. This minus 2, by giving the same denominator, I just end up with a extra 4xn squared times 2 up here. So we have xn to the fourth plus 4xn squared minus 8xn squared plus 4. So there we have that numerator, but now factor this numerator back under the square, and we have this. Since xn plus 1 squared minus 2 is equal to something squared, it can't be negative. So that numerator of term squared minus 2 is never negative. Therefore, this quantity is never positive. So this is never positive. The sequence is monotone decreasing. Now that we know our sequence is monotone decreasing, we can try to show it has a limit. Well, we actually already showed that every term is positive, meaning it's bounded below by 0. So it is a decreasing sequence which is bounded below by the monotone convergence theorem, right there, the limit must exist. So this recursively defined sequence does have a limit. Great, it has a limit. Call it x. Now we're going to manipulate that recursive formula. Okay, if you simply multiply everything by 2xn, on the left you get 2xn plus 1xn, and once you simplify everything down, you end up with an xn squared plus 2 on the right. Now take a limit as n goes to infinity and use proposition 2.2.5. Here, you'll just get 2 times the limit of xn plus 1 is just going to be x, whatever that limit is, but the limit of xn is also x. So 2x squared equals x squared, and the limit of 2 is just 2. In other words, x squared must be 2, so x is plus or minus radical 2. Since every term of the sequence was positive, we know that the limit cannot be negative. Therefore, the limit must be root 2. So we have constructed a sequence recursively that must be converging to the square root of 2. The sequence from the previous example was not totally arbitrary. It arises from a technique called Newton's method, a way to find roots of functions. So for the previous example, the root we were finding was for f of x equals x squared minus 2. The only positive root is root 2. So we're going to make an initial guess. What's the square root of 2? I don't know, roughly equal to 2. This is our first guess for what maybe the solution is. Now for any x sub n, we can use basic calculus techniques. Admittedly, we have not formally justified them in this course, but students will be familiar with them at this point. We make a tangent line. So at any xn, you can compute that the equation of the tangent line is this: 2xn times the quantity x minus xn plus the quantity xn squared minus 2. Now that's just a line. You can easily find its root to be the next guess. So having made a particular guess for a root, you find a tangent line at that value of x. Its root will be your next guess for the root of the function. And you iterate this process, you get exactly the sequence from the previous example. So here is x squared minus 2. We make an initial guess. We know that 2 is a bit too large. 2 is larger than the square root of 2. So at the point on the curve x squared minus 2, given by 2 comma 2, you construct this tangent line. Then you find its root. The root of that tangent line is 3/2. That becomes your next guess for the root of the function. Well, we weren't quite there, so you make a tangent line at x equals 3/2, y equals 1/4, the point on the curve. Find the root of that tangent line, and so forth and so forth. Iterating this procedure gives exactly the sequence from the previous example. Newton's method does have some limitations that one should be aware of. Consider the following recursively defined sequence. x1 is 1, and xn plus 1 is xn squared plus xn. Now if one assumes the limit exists and calls it x, take a limit of both sides, you'll end up with x equals x squared plus x. So whatever the limit is, x equals x squared plus x squared is 0, x is 0, and you say, okay, great, the sequence converges to 0. However, if you just start listing out terms of this sequence, x1 is 1, and look, xn plus 1 is the previous term plus the previous term squared. So it starts to grow rather quickly. From 1, the next term is 2, and then 6, and then 42. It gets quite large, and in fact can never get smaller. Every term is larger than the one before it. Definitely not converging to 0. In other words, if the sequence converges, it converges to 0, but that's a big if. The sequence, in fact, does not converge. Okay, so let's go over some convergence tests for sequences. Now, it's not always necessary to go through the actual formal definition of a limit in order to prove that a sequence converges. We've already seen some powerful tools. The monotone convergence theorem and the squeeze lemma both allow us to conclude that a sequence converges without having to work through the formal definition. Other convergence tests exist to show us that a sequence has a limit. Even if we don't immediately know the value of the limit, for example, in the monotone convergence theorem, you conclude the sequence has a limit, and for an increasing sequence, the limit is the supremum, and for a decreasing sequence, it's the infimum, but you may not be able to compute that immediately. But once you know a limit exists, then you can use some other tools to find what it is. For example, in recursively defined sequences, once you know the limit exists, then it might become easy to compute. Let's move on to proposition 2.2.10. Suppose xn is a sequence, x is a real number, an is another sequence, and specifically an converges to 0. If for all n, you have that the distance from xn to this fixed value x is less than or equal to an, then the limit as n approaches infinity of xn is in fact x. Okay, so let's go ahead and prove it. So this is really just kind of an enhanced squeeze lemma. We have here a squeezing of the absolute value of xn minus x. The hypothesis of the proposition is that this is less than or equal to an, but it is an absolute value, so it's definitely bigger than or equal to 0. Taking a limit as n approaches infinity, we know on the left we have a constant sequence. Our hypothesis is that an converges to 0. Therefore, we conclude that the limit of the absolute value of xn minus x must be 0. Now, let epsilon be positive because this sequence is converging to 0. The absolute value of it minus 0 must be less than epsilon. This minus 0 can be ignored, and the absolute value of the absolute value doesn't really do anything new, so you simply have the absolute value of xn minus x is less than epsilon. In other words, xn is converging to x. Now here's a corollary to the previous that isn't explicitly stated in the text, but I find it very useful to have in our back pocket. Suppose you have a sequence and x is a real number, then the limit of xn equals x if and only if the limit as n approaches infinity of the absolute value of xn minus x is equal to 0. Okay, so let's talk about a few things. As that proposition shows, studying when a sequence has a limit can be replaced with studying when another sequence goes to 0, namely the absolute value of your sequence minus the proposed limit. So in general, it can be hard to decide whether or not a sequence converges, but sometimes there are convergence tests, like the monotone convergence test or the squeeze lemma, that may be useful in telling us if the sequence converges. Here's another such convergence test. We're going to prove a quick result not explicitly stated, just along the way. So here's a proposition not explicitly stated. A sequence xn converges to 0 if and only if the sequence of absolute values converges to 0. Now we had a previous result relating the absolute value of a sequence to the absolute value of its limit, and I remarked it does not go in the converse. Here it is, it's an if and only if, but it's specifically when the limit is 0. So let's get proving. Suppose the limit of xn is 0. An earlier proposition tells us that the limit of the absolute value of xn must be 0 as well. So one direction is immediate. Our earlier result said if a sequence converges, then the limit of absolute values converges to the absolute value. So if the limit is 0, then the limit of the absolute value is 0. We already know that. The only work we have to do is in the converse. So let's assume the limit of the absolute value of xn is 0. Now all we have to do is prove that the limit of xn is 0, so we go through the definition. Let epsilon be positive. Since we know the absolute value of xn is converging to 0, past a certain index m, we have that the absolute value of xn minus 0 is less than epsilon. But again, the 0 may be ignored, and the absolute value of the absolute value is simply xn. So the absolute value of the absolute value of xn is xn, which is the same as xn minus 0. So overall, this quantity here is exactly the same thing as the absolute value of xn minus 0, which we now know is less than epsilon. All right, so we're going to use the previous proposition to prove something a little bit stronger than what's given in the text. It was the reason why I included it. Here's prop 2.2.11, a slight modification from the text. The limit as n approaches infinity of a constant to the n is 1 if c is 1, 0 if c is between plus and minus 1, and does not exist if c is either minus 1 or if c is larger than 1 or less than minus 1. Okay, there's a bunch of cases here to go through. Now for c equals 1, this is most straightforward. If c is 1, then c to the n is just 1 to the n, aka 1. The sequence is constantly 1 and it converges to 1. Now for c equals minus 1, we have the sequence minus 1 to the n, and we've already studied that sequence and shown it doesn't have a limit. So the case of c equals 1 and c equals minus 1, very straightforward. Now let's assume that we're in that middle case. C is between plus or minus 1. In other words, its absolute value is less than 1. Now, the absolute value of c to the n plus 1 is simply the absolute value of c times the absolute value of c to the n, but the absolute value of c is less than 1. So the absolute value of c to the n plus 1 is strictly less than the absolute value of c to the n. In other words, the sequence of absolute values is monotone decreasing. It's also bounded below because its absolute value is bounded below by 0. Therefore, the sequence of absolute values by the monotone convergence theorem has a limit. So we are dealing with this situation right here. C is between plus or minus 1, but we're not directly looking at the sequence c to the n. We're looking at absolute value of c to the n. So in this case, because the limit exists by the monotone convergence theorem, we will call the limit fancy c. If we multiply both sides by the absolute value of c, then the absolute value of c times the limit of the sequence will simply be the absolute value of c times fancy c. But this constant I'm going to factor into the sequence. Now we have the limit of the absolute value of c to the n plus 1 is the absolute value of c times whatever that limit is. However, this is a subsequence of the original. Instead of looking at absolute value of c to the n, so absolute value c, squared, cubed, and so forth, here now we start with absolute value of c squared, cubed to the fourth, and so forth. It is a subsequence. It must converge to the same thing. Now we have the limit equals the absolute value of c times the limit, so I subtract that to the other side and factor. How can the product of two terms be 0? Either the limit is 0, or this parenthetical term is 0, meaning the absolute value of c is 1, but recall that we began this by assuming the absolute value of c is not 1, it's less than 1. Therefore, the only possible solution is that the limit is 0. So the limit of the absolute values, c to the n, is 0. And this is why we had this earlier result in here. If the sequence of absolute values converges to 0, then the sequence itself converges to 0. So under the assumption that the absolute value of c was less than 1, the monotone convergence theorem gave us that the sequence of absolute values converges to something. A little bit of algebra then told us it must converge to 0. And since the absolute values converge to 0, so does the original sequence. So now we started with a constant sequence. An earlier example established this limit doesn't exist, and now we've proved that if c is between plus or minus 1, the limit of c to the n is 0. So that's the second case. Now suppose the absolute value of c is larger than 1. We're going to go through the same thing, the absolute value of c to the n. If we assume this sequence converges to something, then the same techniques would imply that either the absolute value of c is 1 or the limit is 0. But again, we're assuming the absolute value of c isn't 1. So if that sequence converges, it has to be converging to 0. Okay, so if the absolute value of c is larger than 1, then if the sequence of absolute values converges, it must converge to 0. However, the sequence of absolute value c to the n is monotone increasing. Same arithmetic as before, except now, because the absolute value of c is larger than 1, we get that this sequence is increasing. So if a monotone increasing sequence converges, it has to converge to its supremum. 0 isn't even an upper bound of the sequence. Remember, the sequence begins with the absolute value of c, which is larger than 1, so it's certainly not the supremum. So the sequence can't converge to 0, and therefore the sequence of absolute values cannot converge. So if the absolute value of c is larger than 1, the sequence of absolute values to the n can't converge. Now if c is larger than 1, the absolute value isn't doing anything. Therefore, when c is larger than 1, we know that the sequence c to the n does not converge. If c is less than minus 1, we can look at two different subsequences, even versus odd index. Suppose the limit does exist. Call it script c again. One subsequence is made of positive terms. If every term of this sequence is bigger than or equal to 0 and it converges to something, the limit must be bigger than or equal to 0. But the same can be said for the odd index terms, where every term is less than or equal to 0. So if those converge, the limit must also be less than or equal to 0. If the sequence converges overall, both subsequences have to converge to the same thing. We would then conclude not only does this limit have to be bigger than or equal to 0, but that limit must also be less than or equal to 0. Therefore, if c is less than minus 1 and the sequence converges, it would have to converge to 0. In this case, if the sequence c to the n converges to 0, you would know that the absolute value of c to the n must converge to 0 as well, but we already know that can't converge to 0. So, when c is less than minus 1, the lemma of c to the n also does not exist, completing the proof of all various cases of this proposition. Moving along to lemma 2.2.12, called the ratio test for sequences. Now, if you are familiar with the ratio test for convergence of series from earlier studies in calculus, don't confuse it with that. It is definitely related. Let xn be a sequence. Suppose that no term of that sequence is 0. Assume also that if you take the absolute value of the ratio of one term to the previous one, the limit of that exists and is L. If that limit is less than 1, then the original sequence must converge to 0, whereas if that limit is larger than 1, the original sequence is unbounded. Before we get to the proof, let's discuss a few things. If the limit exists but is equal to 1, this lemma makes no claim whatsoever. Okay, maybe the sequence does one thing, maybe it does another. We make no claims if this limit exists and is 1. For example, if xn is 1 over n, if you take the limit 1 over n plus 1 over 1 over n, you will compute that this limit is 1. Also, the sequence xn converges to 0. However, if xn equals 1 is a constant sequence, the limit of the ratios is also 1, but the sequence converges to 1. But if xn is minus 1 to the n, the limit is still 1 and the sequence doesn't converge at all. Okay, so if the limit exists and is 1, we make no claim. Also, if the limit does not exist, of course, we do not make any claim here. Moving on to the proof of this lemma, first let's do the case where the limit exists and is less than 1. So since we have absolute values here, and it has to be bigger than 0, because remember, no term of the sequence equals 0, these absolute values converging to something means that the limit L is not negative. So since L is not negative but is less than 1, pick an R that is somewhere in between L and 1. R minus L is positive because R was bigger than L, so we're going to use this as epsilon in the definition of the limit. Past a certain index capital M, we definitely have xn plus 1 over xn, the absolute value at least, minus L less than epsilon, and remember this was our choice of epsilon. Okay, if the absolute value of something is relatively small, then without the absolute value on the outside, it's between plus or minus that thing. Notice that negative 1 times r minus L is simply L minus r. Now, to be honest, we actually only need the right inequality from the previous slide, and here it is. Notice that you can add an L to just get rid of that from both sides. Then if you multiply by the absolute value of xn, you get that the absolute value of xn plus 1 is less than r times the absolute value of xn. Now this holds past index capital M. So if you keep doing this, starting at index capital M, what you'll see is that the next term in absolute value, definitely positive because it can't be 0, that's one of our assumptions, no term of the sequence is 0, and it's an absolute value, is less than multiplying by r a bunch of times multiplied by the absolute value where you can begin doing this process. So every time you move to the next term, it's less than just multiplying by r, at least if you begin at index m. So this is what you can establish. And this looks marginally complicated, but this right here is just a constant, and this minus m is also just a constant. So we now have the terms of our sequence, at least past a certain point, so we're actually only talking about a tail, but fine. An absolute value being between 0 and r to a power times a constant. But r, remember, was specifically chosen to be less than 1 and definitely positive. So by our previous work, we know that r to the n converges to 0. So by taking a limit as n goes to infinity, on the left we have the constant 0. On the right we have various constants times r to the n, which we now know converges to 0. So by the squeeze lemma, the limit of the absolute value of xn plus 1 equals 0 as well. Therefore, the limit of the absolute value of xn is 0, and we already know that if the sequence of absolute values converges to 0, then the original sequence converges to 0 as well. So the case of L less than 1 is proved. So now let's move on to L being larger than 1. We're going to do a pretty similar construction. Now we're going to pick an R that is between 1 and L. Similar to before, past some index m, we will have that the absolute value of xn plus 1 is bigger than this power of r times a constant. But now r is bigger than 1, so that right-hand side is unbounded. It's a constant times r to a power, but r is larger than 1, and as we discussed in the proof of the previous result, when r is larger than 1 and you take larger powers, it is unboundedly large. So our sequence is bigger than that. It is therefore unbounded in absolute value, so the original sequence must also be unbounded, either above or below. Doesn't matter if it's unbounded, it doesn't converge, and this is all we needed to prove, that the sequence is unbounded. Let's take a look at example 2.2.13. Let's use the ratio test to prove that 2 to the n over n factorial converges to 0. Loosely put, the exponential is growing pretty quickly in the numerator, but the factorial in the denominator is growing even faster. Okay, so we're going to compute the ratio of successive terms. We don't need absolute values because every term in this sequence is positive. So after a little bit of algebra, here is index n plus 1 over index n. This n factorial comes to the numerator. This n plus 1 factorial goes to the denominator. 2 to the n plus 1 over 2 to the n simplifies as 2. N factorial over n plus 1 factorial simplifies as over n plus 1. So we have 2 over n plus 1 certainly converges to 0 as n goes to infinity, so the limit doesn't just exist, it's definitely less than 1. It is in fact 0. So the ratio test says that our original sequence must also converge to 0. Another example. Let's look at the limit as n goes to infinity of the nth root of n to the 1 over n. So we're not going to prove this by relying on logarithms because we haven't really defined or studied them yet. Let's get to working through this example. Let epsilon be positive and consider the following sequence. N over 1 plus epsilon to the n. So epsilon is now fixed, okay, but n over 1 plus epsilon to the n is a new sequence that we're going to look at. If we take a ratio test of this sequence, once we work out the algebra, we get the n plus 1 over 1 plus epsilon to the n plus 1 divided by n over 1 plus epsilon to the n. So first of all, 1 plus epsilon to the n over 1 plus epsilon to the n plus 1 leaves behind a single power of 1 plus epsilon in the denominator. And then I have an n plus 1 over n, which I break apart as 1 plus 1 over n. Now, as n goes to infinity, this is a constant. This converges to 0, so we simply converge to 1 over 1 plus epsilon. Our assumption was that epsilon was positive, so 1 over 1 plus that is less than 1. So by the ratio test, we conclude that this sequence converges to 0. Regardless of epsilon, as long as epsilon is positive, that sequence will converge to 0. So now that we know that sequence converges to 0, there must be some m, so that past that index we have the term of the sequence compared to 0 in absolute value is less than 1. If you refer back to the definition of convergence, there's an epsilon in there, and we're calling that 1. This epsilon was different. It was just baked into this sequence, which we now know converges to 0. Again, the minus 0 can be ignored, and nothing negative is happening here. So we end up with n over 1 plus epsilon to the n is less than 1, aka n is less than 1 plus epsilon to the n. And once I take an nth root, n to the 1 over n is less than 1 plus epsilon. So for every epsilon, there is an index past which this inequality holds. So now we know, regardless of epsilon, as long as epsilon is positive, eventually this inequality holds. Since n is larger than 1, n to the 1 over n is definitely bigger than 1. So past a certain index, n to the 1 over n is between 1 plus or minus epsilon. In other words, its distance to 1 is less than epsilon. So regardless of epsilon past a certain index, this inequality holds. That is exactly the definition, that the limit of n to the 1 over n is 1. Okay, let's talk about that. So as an exercise, you can look at the following sequence, 1 plus 1 over n to the n. Can you show this sequence converges? Don't worry about what it converges to. Just try to prove that it converges to something. So one approach is through the monotone convergence theorem. So you need to show not only is this sequence monotone, it happens to be monotone increasing, but you need to establish that it's bounded above. Don't worry about trying to find a really great upper bound or an optimal one, just an upper bound. So let's refresh what we've done in this section. Limits interact very nicely with inequalities. Okay, the squeeze lemma, very useful. Remember, however, that strict inequalities in general are lost when one passes to a limit. If you have two sequences with a strict inequality between them, you do not inherit the strict inequality in the limit. You must introduce the possibility of equality. Convergent sequences also work nicely with algebraic limit laws. The limit of a sum of sequences will be the sum of the limits. Same for differences, products, quotients, roots, absolute values. For some of these, like quotients and roots, there are some assumptions you need to throw in to make sure everything is actually defined and reasonable, to make sure you don't divide by 0, etc. But other than that, these limit laws work just like you would hope. Recursively defined sequences play pretty well with limits and give themselves up to some nice study and nice examples. And finally, there are some convergence tests like the ratio test. There are more convergence tests for sequences. We have certainly not exhaustively shown all of them, but we've hit the major ones.